Alright, we're still in 15.7. This is the last recording. So first of all, let's review 15.3 just a little bit here. So when we talked about double integrals, and we talked about usually we would find area by a single integral, but we could actually also find it with a double integral by noting that if we let z equal 1, and then we just integrate over the domain, then that gets the area of the domain. And so you could think of it as, again, a cylinder would be an easy case that if this is for a z of 1, then the equation of the cylinder, the volume is going to be the basal domain pi r squared times the height. But if the height is 1, then the volume you get is pi r squared, which is the area. And so that was just kind of a cool little trick that we could use double integral to figure out area. So it's a volume, but again, with that specifically, with that z equals 1, then we can also think of it as the answer as area of the domain, D. So we're going to use that same concept, but we're going to bring it up a dimension. So we're going to find the volume of our domain space, E, which is in 3D. It's a solid in 3D, by just taking the triple integral over it of 1. And that's it. So we can use a triple integral to find volume. Another way is we could use a double integral, where our function here is something other than 1. But this is a way that we can do it. So an example would be using a triple integral to find the volume of a given solid, the solid enclosed by the paraboloids y equals x squared plus z squared and y equals 8 minus x squared minus z squared. So we're going to use this new triple integral trick, and we're told to do that, so we're all set up. And so something to note is that both these paraboloids are written y in terms of x and z. So this is a pretty strong indicator that our innermost integral is going to be in terms of y. So working on that, we need to find the bounds of y, which one is the least and which one's the greatest. So one thing is these equations of paraboloids are fairly simple. This one especially, y equals x squared plus z squared. Notice it's centered on the y-axis. If you let x and z equal 0, you get y equals 0. So this is going to be at the origin. And then if we let x and z equal 1, we're going to get y equals 2. And this is the radius of that circle that we're going to have in the xz plane. This other one here, we have minuses with the x squared and the z squared, and if you just again see what's going on at x and z equals 0, then you're going to get 8. And so this is going to be at least at xz being equal to 0, it's going, or x and z being equal to 0, the surface that's going to be greater is the second one here, because it's 8. And then our first paraboloid is 0 when x equals and z equals 0. So we're kind of pretty sure that our bounds are the first paraboloid is the least, or representing like the least or furthest to the left surface, and then we have our surface on the right if we're looking kind of this traditional orientation. Well, not directly to the left and right, but this is what it ends up looking like. So we have our variable bounds and we can plug those in. We're just integrating 1, or if you want to leave it just blank, that means the same thing. And then the intersection of these two paraboloids is pretty important. This is going to happen when the two paraboloids are equal. It's important because this is the widest part of these intersecting surfaces, defining our solid, and then on the xz plane, eventually with our integral, we're going to have to define that domain in that plane. So, and that's the widest part. So we project down that widest part, and that's our domain D that's shown in green, and that happens at the intersection of the two paraboloids. Fortunately, they're all solved for y, both of them, so you can just easily equate them and then do some algebra to see what's going on. And note that that intersection is a circle in the xz plane with a radius of 2. So we have a lot going on here. The domain D that's in green is going to be what we're going to do with our outer double integral. At this point, it might be good just to handle this innermost integral of your triple integral and then start looking at your domain D and piecing that together after you've taken care of the innermost integral. Then it'll be a pure double integral that you can handle. So that's an easy integral. We just get y, and then we're going to plug in with our limits of integration there, do some simplifying, and then this is where we have a double integral. We've taken care of that innermost part of the triple integral. So let's now really focus on our domain that's shown in green here on the xz plane. We still have to integrate with respect to x and z, but notice that it would be easier to do in polar, just like the last example. So our domain is a circle, x squared plus z squared is less than or equal to 4, so it's a radius of 2, and really similar to the last example with respect to how we can set this up in polar. Our theta is going to sweep from 0 to 2 pi. Our dA is going to be r d theta dr, or dr d theta, doesn't matter. But whatever order you pick there, make sure you're keeping your integration limits here over the polar rectangle consistent. So if I have my theta here in the innermost set, then I put my limits of integration with theta in them there. This one I decided to do it a little bit differently than the last one, in that notice I have completely in the integrand function in terms of r after simplifying and whatever. And so I can actually break this up into two integrals and just integrate one with respect to d theta or over theta, and then I have the integral in terms of r. It's a little bit of a time saver, so I do this evaluation, simplify my result, and I get 16 pi. So that's it for this section.